6% probability. Now, do you understand that all 80 of these, so these 80 come from 50/40, right? All 80 of them will map to one shape. How many shapes do we have? 429. So all 80 of them will map to a single shape. No other ones will. So what's the probability of getting this tree? It's going to be 1.58%. What's the probability of getting this tree, this one right here, this skew one? Only one sequence. It's going to be 1 divided by 50/40. That's going to be 0.2%. So you can see different shapes, the different probabilities. So, let's say the probability of shape I is equal to P of SI. So the probability of shape I is equal to P of SI. So we know, let's say the probability of a full tree where n is equal to 7, we know that probability is equal to what we just did a second ago. We had 80 over 50/40. The probability of a tree looking like this equals to 1 over 50/40, right? So this tree is one of the possible shapes. This is one of the possible shapes. Do you think this is easy or hard to do for the general tree 8, 9, 10, 20, and it's not easy, right? There's some real patterns in here that you have to figure out, which I would never ask you to do. But you can see that there are patterns. So I did 7, because 7 is something we can attempt to do with some level of success. So we can try to figure out some probabilities, likelihoods. So it turns out that each tree has its own likelihood. So this is the interesting thing here. I would love to do the probability of a full tree, because that's an interesting analysis, how we did all the splits and everything like that. If you did this for 15, and if you're crazy enough to do it for 31, you would start to see a pattern. You would start to see how those factorials are coming up. There's going to be patterns of factorials. And then I can say, what's the probability of having 63 nodes and what's the probability of getting a random tree of 63 nodes being balanced? Well, it's going to be a lot of different permutations, but there's also going to be a lot of possible permutations. 63 factorial, which is ginormous, just horrendously large. All right, so one of the things that we did last class is that we decided that the complexity of building a full tree with n nodes was theta, what? What was our probability of building a full tree? That's what we spent all the time on. Remember, we had the BBT, and then we said, how do we analyze it? So we ended up doing a summation. On that left side of the board, I to the I, as I went from 0 to LG n minus 1. And the answer was theta what? And log n. I'm just going to put natural log, although we had LG. It makes no difference because all logs are proportional anyway, so LG is proportional to ln, and theta is proportionality anyway, so it doesn't matter which log you choose. That's it. It means that if I have n nodes, okay, then the number of comparisons is equal to what? N log n. So if I take this n log n and then divide it by n, that gives me the average number of comparisons. What does division of this do? If this is the number of comparisons to build a full tree, then this is the average what? How many nodes are coming in to build a full tree here? Okay, so this is the total number of comparisons, right? Total number of comparisons is n log n, proportional to that. How many nodes are there?
N.
So if I divide it by the number of nodes, what will this mean? So ln is what? ln of n is what?
Average.
The average number of comparisons per, the average number of comparisons per node. Well, if the average number of comparisons per node is ln, that means on average, each node is only going to ln comparisons, which makes sense since the height of the tree is going to be basically ln minus 1. Would you call this the best case or the worst case? Or the average case? The average number of comparisons per node is ln, with n nodes being inserted into a tree. That's really the best case because the tree is coming out how? Balanced. Or full in our case, yes, balanced or full. So that's really the best case. So the question is, can we expect the best case to happen? Well, we found out that 80 divided by 50/40 is what? What was that percentage again? Not very high. Let's do it again. So I'll do 80 divided by 50/40. Maybe you guys have it here. I came up with 1.6%. 1.6%. Now, do you think the probability of getting a full tree with 31 nodes, 63 nodes, 1,023 nodes, do you think that probability is going to increase or decrease over 1.5%? What do you think? That's a good hypothesis. It's not right, but it's a good hypothesis. It could be tested. We have no way of knowing otherwise, right? Okay. Let's take 1 out of 50/40. I think we must have done this wrong. Yeah. Remember we did 1 out of 50/40? That this tree, this particular tree, the probability, I had it wrong, I gave the wrong number, is because I said it's too high. It's 0.02 of 1%, which is 2% of 1%, which is, oh, shouldn't have done that. There's something there, so. Which is 1 in 10,000, 2 in 10,000. 2 in 10,000 is the probability of getting this tree. So this tree is less likely than a full tree. Are you surprised? So this shape is the probability of 1 in 10,000. But this shape has got a higher probability. It's 1.5%. It's 1.5 in 100. Much more likely. But now I'm going to ask you this other question. What's more likely, a skew tree or a full tree with 7? And I don't expect you to give me an answer, but what do you think? How would you test it? How would you test if what's more likely, a full tree or a skew tree with 7? Not a skew tree like this, any skew tree. Now you have to what? Find out what? Would you agree that this has only one sequence that's going to give it to me?
Yes.
Would you agree that if I go from here, here, and then I go this way, there's only one sequence that's going to give it to me? Think about it. It's going to go root 1 larger everything less. So that means that the right child of the root is bigger than the root. Is bigger than the root. Okay? But then all the remaining nodes are going to be are also bigger than the root, but they're going to be in descending sequence less than this one. There's only one such sequence. In fact, can we prove that every skewed tree is generated by one sequence? Is that really true? What do you think? I'm not going to ask you to prove it. I'm going to ask you to guess. Do you think that any skew tree is generated only by one sequence?
No.
Well, let's look at a couple of examples, see if we can gain some intuition. So let's look at this. Let's look at this sequence. 1, 2, 3, 4, 5, 6, 7. And let's say the numbers are all different. So the only numbers we have to choose from is 1, 2, 3, 4, 5, 6, 7. What does this value have to be? Have to be. If the keys are 1 through 7,
7. No.
this has to be 7. You're right. So let me scare you. Yes, 7 is correct. Because everything is less than that. Now, you can see here that these values are, no, forget about this value. These values, look, consider this imaginary, special, unknown value. How do these keys relate to this value? How do these keys relate to this value? So these are increasing over this value. So they are less than the 7, but they're greater than this value. All of them are greater than this value. All of them are greater than this value. Well, we only have numbers 1, 2, 3, 4, 5, 6. So what value does it have to be?
1.
Can it be 2? No. Why not? Because if it was 2, then 1 would go to the left of it. So it has to be 1. So that means that has to be second in the insertion sequence, otherwise it doesn't end up here. And in order for this one to be a third insertion sequence, it has to be, they're all less than 7, because they're 1, 2, 3, 4, 6, 7, and 1 and 7 are already used. So what number could this be? Could this be 3? No. Could it be 4? No. Because if it's 3, 2 is going to go to the left of it. So this number must be 2. Could this number be 4? Why? Because 3 will go to the left of it. So it must be 3. You see what I'm saying? Could this be 5? Must be? Could this be 6? If it's 6, then 5 is going to go here. We're going to get that shape. So it has to be 5, it has to be 6. So it appears that this skew shape has a unique sequence. Okay? We also know that this is a unique sequence. Let's try a different one, shall we? So let's try this one. 1, 2, 3, 4, 5, 6, 7. What key does this have to be? 7. Because everything is in the left subtree. Now, I don't know what key this is, but everything in this subtree is greater than that one. So this number has to be 1. Okay. And now, look what I have. I don't know what number this is. It's either 2 through 6. But whatever number I have, everything else has to be less than that. So what is the left number in the sequence that is everything is less than it?
6.
So it's going to be 6. Could it be 5? No. So 6 is going to go this way. Okay. Could this be 5? How about 4?
No.
If it's 4, then 5 will go to the right. So it has to be 5. And 4. And 3. And 2. Would you agree that this has only a single sequence? Okay, so let's hypothesize that every skew tree has a unique insertion sequence. Let's assume that's true, without proving it. By the way, this is not a proof, is it? No. Does it look like induction? No. Does it look like contradiction? No. Direct? Indirect? No, no, no. But this is called what? We haven't disproved it. So we've shown 3 examples where it's true. So this is called what? What do we call that? Well, we call it anecdotal evidence. Have you heard of that? Matt? can't. Somebody better help me with the spelling of that anecdotal. Okay, you're from Harvard, right? You gotta help me with the spelling of this one. Anecdote.
Can't do it.
You can't tell me? I just want to spell it correctly. And I think it starts with an N. I'm going to spell it this way. I'm going with the Latin. Okay, anecdotal. So anecdotal evidence means, you know what anecdote is? Anecdote is like a story. I heard that the Joneses just got a really expensive refrigerator. I think it's a GE model XL. Okay? It's like a story. And you tell somebody else, kind of a rumor, anecdote. We talk about it. And all of a sudden everybody thinks that they got, maybe they got a dishwasher instead. Okay, but it's probably just an anecdote. So an anecdote is a story about something you observed. So I observed 3 different sequences, and they all had unique sequence orders. Therefore, I'm concluding all skew trees have a unique sequence order, because I'm citing anecdotal evidence and I don't know how to prove it. So your further work will all be based on the truthfulness or the validity of your assumption based on your anecdotal evidence. So anecdotal evidence is something that points to something but does not actually prove it. Okay, so it falls short of proving it. It shows example after example after example. So how many skew trees are there out of 7 nodes? Because maybe we can show it for all of them. In fact, we could follow and generate all of the possible skew trees for 7 nodes. And maybe we could show that they're all generated by unique sequences. And if we do that, we still have not proved that skew trees are generated by unique sequences, because that's only true for 7. Maybe if you have 8, it changes everything. So it's not a proof. So the proof would have to be the general proof. That's why we need proofs like induction and contradiction, etc., 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 or maybe even direct proofs. Okay, but let's make the assumption based on this anecdotal evidence that in fact every skew tree is generated by a unique sequence. Can we count the number of skew trees we can generate? Well, I do know this. Every skew tree starts off with a root. I can prove it, but I'm not going to bother proving it to you. Okay. Now, some skew trees that have a height of 2 go like this, but others go like this. Not at the same time. They either go like this, or they go like that. So that means to get to level, so I have one choice to get to level number 1, which is the root. You just add a root. But once I add the root, I can move to the what or the what? I can move to the left or the right, therefore I have 2 choices. Are you with me?
Yeah.
So what I'm going to do is I'm going to show those 2 choices like a full tree, but in reality only one of them is going to be valid. Are you with me? So now, this tree has a height, this tree right now has a height of 2, and the number of nodes is 2. It's either going to be 1, 2 or 1, 2. Now I'm going to go to height number 3 or depth number 0, 1, 2. And I have how many possible choices? Well, if I went in this direction, I would have 1, 2. And if I went in this direction, I would have 1, 2. So I have 2 choices to get here. And so therefore, how many choices do I have here? 4. And what do you think we're going to do with this 2 and the 4 and the 1? We can multiply them. Let's see what that means. So let me ask you a question. So let's say we are multiplying them together. What's the product of all these? The product, so pi is the product. Pi is the product. The product of I is equal to 8. 1 times 2 times 4. The product of I is equal to 8. So we have, let's see, that's making sense. Let's see. So we have 1 here, 2. So it's not quite right, is it? 3, 4. How many trees do we have? 4. So it's not 8. So what should we do? That's what we're drawing the diagram for. So what tells us how many skew trees we can have? Would you agree that here we only have one way to make a skew tree? Now here, we have 2 ways of making a skew tree of 2. So 3, we could go here or here, here or here. So that means with 3, we have how many choices? We're going to have 4 choices. So it looks like this is the number we look at and we don't multiply. So it's a little bit different than the shapes, right? So 4, and now, each of those 4, however we do the 4, because this could be, so next one could be 1, 2, 3, 1, 2, 3. This could be 1, 2, 3, or 1, 2, 3. So we want a skew tree. How many ways can we make a skew tree of height 4? Well, there are 4 of height 3, right? 1. We cannot add here, cannot add here, can add here. Or here, here, or here, here, or here. How many? 8. Now, what is the height of a tree? What is the height of a full tree of 7 nodes? What is the height? The height of a full tree with 7 nodes. 1, 2, 3, 4, 5, 6, 7. So the height is 3. Did you say 3? You did say 3, right? Okay. So therefore, how many? So height of 1, height of 2, height of 3 is 4. So that's all we have. So the question is, what's the probability of getting a skew tree with 7 nodes? Easy question. What's the probability of getting a skew tree out of 7 nodes? Well, how many skew trees are there with 7 nodes? Well, I'm sorry, with how many nodes did I say? With 7 nodes. We haven't do that. We haven't done that yet, right? So this is going to be 1, 2, 3 nodes, right? 3 nodes. Then what's going to happen here? So number of nodes. This is going to be 1. One way to get a skew tree. 2 nodes. There's going to be 2 skew trees. One this way, one this way. This with 3 nodes, we're going to get 4 skew trees. How about with 4 nodes? 8. How about with 5? How about with 6? And how about with 7? There's your homework answer, part of it. Okay, so there are 64 skew trees. So let me ask you a question. What is the higher probability from a random sequence of 7 nodes? A random sequence of 7 nodes is going to get inserted into to create a binary search tree. What has a higher probability, a skew shape or a full shape? Go back to your notes in the beginning of the class, because we discussed it. What is a higher probability of happening? A skew tree or a full tree, giving 7 nodes in random sequences? Go ahead. So a full tree has a higher probability. Why? Because 80 sequences out of 50/40 generate full, but only 64 out of 50/40 generate skew. So it's more likely to get. So if we add, what I'm going to do is I'm going to add 80 plus 64. That's going to give me what? 144. What's that equal to? 80 and 64 is the number of skew, of sequences that produce either skew or full. If I divide it by 50/40, I get, I'll round it up, 3%. So if I take a random sequence of 7 nodes, 3% will be either skew or full. So 97% will be what? 97 will have a height of between what and what? 97% will have a between a height of what and what? They're not going to be skewed, so they won't have a height of what? They won't have a height of what? So they must be a height of what at most? 6. And they could be as short as what? So 97% will have a height of 3, between 3 and 6.
But the height of 3 is the full tree, so.
Height is the full tree, that's what I'm saying.
Yeah.
So, okay, so it's going to be 4.
Yeah.
Thank you. Between 4 and 6, she's absolutely right. So, yeah, 97 of them between 4 and 6. All right, so the last thing I'm going to show you right here is basically, I'm going to let you read through these notes, but I am going to, let's take a look at this expression. So how would we compute the average number, you see, if we add up the depths, so what we're going to do is we're going to take an average tree. An average tree means a random sequence is being inserted into the tree. We're going to add up the depths of the nodes. We did that last time. If we add up the depths of all the nodes, we're going to find out that the depths of the nodes of a full tree is n log n. And when we divide it by n, then the average depth is going to be log n, which is going to be right at the perfect level that we want it to be at. So now we're interested in what happens at a random sequence of insertions. And so what we're going to do is we're going to do something very similar to what we did before. So our expression is the sum of the depths of the nodes of an arbitrarily generated binary search tree with n nodes, we're going to say is equal to, now look very carefully what I'm going to do here. It's very similar to what we had before. It's going to be the average depth of a random tree with 0 nodes plus the average depth with n minus 1. Remember, I have n nodes. So what I'm doing is I'm splitting this into the left subtree and the right subtree, like I did before. I'm splitting this into the left subtree. Left has 1, right has n minus 2. Why? Because d of n is n nodes. That means the nth node is the root. So that I have 0 on the left, n minus 1 on the right. Or 1 on the left, and n minus 2 on the right. Or 2 on the left, and n minus 3 on the right. Or 3 on the left, and n minus 4 on the right. And then I'm climbing up, n minus 2 on the left, only 1 on the right, n minus 1 on the left, 0 on the right. So what I'm saying is that the average depth of nodes with n nodes is equal to an equal likely split of the subtrees. So I'm dividing it by n, because basically there are going to be n parentheses expressions here. I'm letting them, each of them be equal or likely plus divided by n. Now I'm adding to it plus n minus 1. Does anybody know why I'm adding n minus 1? This is very important, but I'll explain it to you because I'm not going to make you suffer too long. So the average depth of a randomly generated binary search tree with n nodes is equal to the average of any split of the average tree, equally likely, going in any direction, plus n minus 1. Now let me ask you a question. If I have a tree of any shape that has n nodes, how many nodes are in the left subtree plus the right subtree? N minus 1. So therefore, if you look at the depths of a subtree, if you look at only a subtree is off of the root. If you look at the depths of the nodes of the right subtree, the root of the right subtree is a depth of 0. But in reality, when you put it in context of the actual tree, its depth is actually 1. Because the root is really depth 0. So the left subtree, its root is 0, but really it's actually 1. Because it has to be rooted off the actual root. Make sense? So in fact, if you consider one node as a root, suppose I have 7 nodes on the left and 8 nodes on the right. If I sum the depths of these 7 nodes within their tree and the 8th node within their tree, I will get the sum of the depths of the subtrees. But actually, all of them is 1 deeper because they're connected to the root. And that's why the plus n minus 1, I'm simply adding 1 depth count for each of the nodes in the left and right subtree. That's the recurrence. And interestingly enough, this recurrence is not close to, but it's almost identical to the analysis we did with quicksort. So notice that we have, so this is what we have here. Then I combine this stuff in here as a summation. Then I can see that it's symmetric, so I double it. So it's going to be di twice, from 0 to n minus 1, just do it twice, divided by n for equally weighting, and then add all of the extra depths. And then we're going to get this equation. We're going to now multiply this equation by n. Let's multiply both sides by n. So we multiply this by n. We'll multiply this by n. This already had an n in it, so it disappears. This didn't have an n, so it appears. And then we'll copy this formula and substitute this formula for n equal to n minus 1. N minus 1. N minus 1. N minus 1. N minus 2. And now we do this to get subtraction, or what we call telescope, so we cancel the terms. And so we're going to subtract equation h from equation 7. So it's going to be this one minus that one. Okay, and as we simplify it, and we divide both sides by n times n plus 1, we get this recurrence, which is almost identical to what we had in quicksort. So we're going to take this equation, and it becomes equation 10, and equation same is as equation 3. It's the equation from quicksort. We get the same exact equations. So at this point, we can see our analysis for the sum of depths of the nodes.